Hi everyone, here we are again doing some replication exercises. This time we're replicating the geographically weighted regression analysis published in the Journal of Peace Research in 2010. And we have already done the replication in the standalone software package GWR4. Now we are doing the same replication in R. So in terms of preliminaries, we're going to be doing the same replication across several different platforms or environments. Again, we've already done the first one involving Geoda and GWR4, having to do some transformations in Geoda, generate the XY grid reference that's necessary for GWR4. Now we're moving to R, and then the last video after this one, we'll do the same replication in Python. All of the replication data was obtained from the replication data sets on the JPR website. I encourage you to look at that to find some other data if you're interested. Also, the original replication file included only the non-spatial data, an Excel file with the attribute data for each unit, but no spatial identifiers. So I had to generate a new shapefile and do some various, or obtain rather, a new shapefile, and then restructure the shapefile, dissolving and deleting some units to make it align with the non-spatial replication data. All of that data was joined, and that's the replication file that we are now using. At this point, I assume that you've downloaded and installed R on your computer along with all required packages. R should be a familiar environment to you by now, as this is the fourth replication that we're doing in class. Also, all of the replication data, the original article, R script are on the Blackboard course site. Following the replication assignment, these are the steps that we are going to carry out. We're going to focus on the empirical results, so that involves the descriptive map in figure 4 showing the distribution of the aggregate terrorism index labeled T in the data. We're also going to generate a grid reference for the standalone GWR4 software. We needed to generate that set of coordinates or that grid reference in another environment. So we had to extract the XY coordinates of the centroids in Geoda. We could have done it in another software environment, but we chose Geoda since we're familiar with that one. In R, however, we can do this internally with a single line, so we'll see how to do that. And then we're going to replicate the main set of results reported in Table 1, the OLS or global regression, and the GWR results. And then finally, we'll visualize the main set of results, the local coefficients, by reproducing figures 5 through 8. Throughout, we'll discuss multiple diagnostics, so we'll keep coming back to this issue of motivating the geographically weighted regression. So let's go to the original article, the replication assignment, and then move into R. This is the original article, just as a reminder, and we're trying to reproduce several main empirical findings. These are the first few descriptive figures, so we want to reproduce figure 4 on the bottom right, which shows the distribution of the geographic distribution of the aggregate terrorism index. And then we want to move to table 1 and reproduce all of these results here. And then we want to reproduce the local coefficients, the maps of local coefficients. So here you see the local coefficient of the base per capita income, one of the main predictors, the local coefficient of terrorism on the right, and then in the next set of maps on the next page, we see the local coefficient of education and the local coefficient of G, or government expenditures. So we want to reproduce all of these maps and discuss them in relation to the rest of the other empirical findings. So our first thing to do then, our first task, is to reproduce the maps, the spatial, especially mainly figure 4 here, the geographic distribution of the aggregate terrorism index. We'll always be referring back to the replication assignment. So if you have any doubts, just keep coming back to this replication assignment. The variables are described here. There's also several notes on that page about how I reconstructed the shapefile from having obtained an original shapefile and then restructuring it. And then the actual replication items begin here, right, with figure 4, as I said. We need to construct our grid reference and then table 1, etc. So let's begin with figure 4, or at least let's begin in the R environment and start working our way through these steps. So here we are in R. I'll just clear the console here, and this is our R script. You should have downloaded this from the Blackboard site, or I circulated it by email. You see some preliminaries here, just identifying the R script. This is just good practice to keep any audience that might see this script abreast of what you're trying to do. I've got a brief outline of what the R script covers, some helpful commands as usual. And now we want to make sure that all of our that R is current, our version of R is current, and that all of our packages are installed. I've already done this, so I won't do this right now, but you should go ahead and install any missing packages and then open them with the library command. You want to make sure you've got your working directory set correctly, so if you don't know what that is, use this command, get working directory. Here I can see that I'm in the right working directory for this particular replication. Just make sure this is set to the working directory on your machine, not to mine. This is my file path. So change that, and then we can see what files are in that working directory. So here we see the merge 3 version of the shapefile, which is the final restructured version of the shapefile. Merge 4 is here. This is just what I've outputted at the end of replicating my results, so ignore that for now. We'll come back to that in just a second. Then you want to read your shapefile in. You can check to see if the shapefile is available in the and what its description is. So if you can access this shapefile information, then that means you've got the file path correct and you can load it. And then because we have the projection component, the PRJ component up here, you can see it in the directory. We want to use read OGR. So read OGR requires the file path. So one easy way to do that is just to set an object equal to the file path. That's what I've done here. Created a new object called path with the file path. And then I'm creating a new object called SHP, or shape, with the read OGR command. The file path, the name of the shapefile without the file extension, without the .shp, and that should load. So we can execute it all at once, and there you see it as loaded, and gives you the fact that it has 67 features and 27 fields. We could use another command if we wanted the read shape spatial, if we didn't want to load the PRJ command, the component, but let's just stick with the read OGR. We can summarize now the shapefile. You can see that it has the names, object IDs, etc. And then we can come back to the script here and create a new data object with the data frame. I'm just hitting Control R here as usual. We can look at the names of all of the fields. We can look at the first 5 observations. We can look at the last 5 observations. And we can attach the data so that we can call it without having to call the shapefile every time, or the data frame. Here's some additional commands. You don't need to use these. If you wanted to write a new shapefile, you could do so. You don't need to do that right now. If you wanted to write a new shapefile with a PRJ component attached, you could use write OGR. We don't need to do that right now. If you wanted to generate a projection component, you could also do that. We don't need to do that right now. So let's just check our geometry and see if we can generate a version of figure 4. If we plot our shape object, here it is. We can see that we can check our geometry. That's our basic geometry. Again, if we go back to the original article, that's just a quick visual check that we're working with the right geometry. We could generate a slightly more advanced version of this plot with the provincial names at the coordinates, at the polygon centers. That's what this looks like. So that's again a nice visual check. This also provides the axes so that you know what kind of longitude and latitude you're working with. And then we could also look at the um, get a better sense of the distribution of our variables, especially if we wanted to reproduce figure 4 here. Figure 4 is essentially giving us a sense of the geographic distribution of the variable. But if you look at the legend, you can see that there are a lot of 0 values, and then the values seem to be concentrated on the upper end, right? Uh, so just this legend alone makes me wonder about the distribution of the values. It looks like that almost half, maybe more than half of the values are 0. So we want to see what this looks like. One quick way to do that is to look at a histogram of the variable. So we could do a histogram. This indeed confirms that it looks like over 40 of the 67 units have 0 terrorism incidents, and then there's a couple on the far end that have a lot. So this is a fairly skewed distribution. We could then create an object with 6 quantiles or 6 divisions and try to graph this using this block below. That's what this looks like. Again, this kind of doesn't give us, it's not very informative since the data are fairly skewed, but if we use the SP plot, we might get a better sense of what the data looks like. That's this graph. Again, not too much variation. We see a lot of low, these are all your zeros, the very dark areas, and then one very high area up here. This is Istanbul, or part of Istanbul in our shapefile. So it looks like terrorism is concentrated in Istanbul. Maybe there might be a few terrorism incidents in the southeast. We could do a couple more plots using the sp-plot command. This is a slight variation. Now we've got a title. Still looks like our terrorism is heavily concentrated in the northwest province of Istanbul, but there's a few terrorism incidents also in the southeast. And then we could finally do one more sp-plot. This is maybe the more flexible command, making the provinces with more terrorism incidents darker. That's a little bit more intuitive. So now we can see that there's 3 provinces in the southeast that have around 10 or between 5 and 10 terrorism, or have a score of between 5 and 10 on the terrorism index. The province in the middle here, I believe that's Ankara. We could plot this with the names again to see what that is. Yep, or Ankara. I'm unsure how to pronounce that, but let's go back to our reds plot, and you can see that there's also that province also has a score of between 5 and 10, and then Istanbul again has a score of above 25 on the terrorism index. So this is the closest, this plot is our closest approximation to figure 4. Again, here is figure 4, and let's just focus in on it here. We can see them side by side. And generally speaking, the distribution aligns, right? The dark blue in this graph makes Istanbul and Ankara and the southeastern provinces and some southwestern provinces stand out. But on this terrorism index on the right, it really looks like terrorism is concentrated in these 3 southeastern provinces, the central province of Ankara, and then really heavily concentrated in Istanbul. So we've just completed this first replication item. We might want to answer or think about some of these questions, but let's keep going, constructing our grid reference and then moving on with the OLS and GWR analysis. So in R, moving forward with the script, we could check for some correlations in the data. This is just some familiarization with the data that you might want to do on your own. You could plot some correlations. One of the things that we might want to do is is to plot these correlations just to see what the data look like in case there's a risk of multicollinearity. This is what those plots look like. At this point, we might be a little bit concerned, say here, about a correlation between base income and education. That looks fairly linear. If we looked at the correlation data itself, you could see that these are correlated fairly heavily here at 0.72, right? So that's a little bit of a concern, so we might want to keep that in the back of our mind. But let's keep moving forward and just execute the OLS analysis. So this is the command for executing this linear model. Again, growth is our dependent variable. Here are our independent variables, and we've already called the data intuitively. So let's execute this command and then summarize our model. And here is our OLS result. We could compare this to table 1 in the paper, and here is table 1. So we could put these side by side, and you see the intercept has an estimate of about 1.6, and there's the constant there, about 1.5. Base income, negative, statistically significant, negative. The magnitude is off a little bit, 0.5 reported in the paper, negative 0.5, and we have closer to minus 0.3. The terrorism index has the expected, right? This is the main relationship of theoretical interests, and so they find that terrorism, as expected, as terrorism increases, economic growth decreases, right? That's the negative relationship. So they find negative coefficient 0.007. We find negative 0.006. That's quite close. But they find it significant at the 95% level, and we find it significant barely at the 90% level. Then education is significant. For us, education is not significant. For them in the OLS model, the magnitude and the direction is the same, and government spending is significant for them, but not significant for us. And then the coastal variable is significant for them, but not significant for us. So we've come very close in replicating some of the findings and the distribution of the data, but several of the significance levels are off between our results and their results. Let's keep moving forward with the OLS. I've got a couple of non-spatial diagnostics you could run on your own if you want, but let's move forward with the GWR. So every geographically weighted regression requires a grid reference. That's the XY coordinates. We could generate these in another program, any GIS program, ArcGIS, QGIS, or in Geoda, and import them. But we can also generate them internally here with just this line here. So we're going to generate a new object called coords by using the coordinates command, extracting the coordinates from our shapefile. So we can run that, Control R, and see what they look like. Here they are, right? So here is in the first column of this object, our X coordinates, and in our second column are our Y coordinates. So this is quite nice, quite quick. If we had two variables that we had extracted from another program, say our X centroid or our Y centroid, we could bind them together, two-column object, and call that X grid table or call that coords. The next step is to check for non-stationarity. Now the only motivation for the geographically weighted regression is that you expect, as with a spatial regimes analysis, you expect that the coefficients in what are going to vary in their magnitude, direction, or statistical significance in some meaningful way from one unit to another. That is contrary to the OLS model, which assumes or estimates a single average effect for all of your units. you're saying that that's not true. The effect is not stationary. It's not even. It's not the same across all units. It's different, and it's different in a statistically significant manner. So one way to test for that, to see if that is indeed true, is to do this randomization test for stationarity, or Monte Carlo test for stationarity. It's part of the GW package that I'm citing here at the top of this section of the script. So here's some sample code from Roger Bivand, but here's the code applied to our JPR example. So we want to create a distance matrix. That's what this command does. You can see it execute in the console up on the left. Then we want to create a bandwidth. This is our moving window or neighborhood that's going to keep shifting. For each unit, it's going to find a neighborhood of other units and then run a regression and estimate a coefficient, estimate all the coefficients for that unit. Then it's going to shift to another unit, find that same neighborhood or the respective neighborhood, and run the regression again. So this bandwidth establishes the size or the composition of that moving window or neighborhood. So we can generate that. Here it's optimizing that bandwidth. So it finds a bandwidth of 12.89. There are multiple different kinds of bandwidths. I have some various comments down below. We'll talk about that in just a second. So we create one here that is fixed. So as in this case where adaptive equals false, it's fixed. That means it's finding that window or neighborhood based on a fixed distance band. So it's finding a distance, and then it's finding all of the neighbors within that distance. If you say that adaptive is true, then it's going to find the number of neighbors, or the number of some number of nearest neighbors, some optimal number of nearest neighbors. So the distance might flex, right? So it might adapt for each spatial unit. That's why it's called adaptive. So we've just generated a fixed bandwidth. This next block generates an adaptive bandwidth. And you can see that it checked with 49 nearest neighbors, 38 nearest neighbors, 56 nearest neighbors, and it settled on 63 nearest neighbors. Notice that this is nearly the entire sample, so we'll talk about that, about what that means. Next, it's going to run a randomization test to see if the coefficients vary in some statistically significant way across units. So we can do that with the fixed bandwidth. That's this test here. So we'll run this. May take just a minute. There it is. And then we're going to run the one with the adaptive bandwidth, and I'll talk about them both in just a second as soon as it finishes running. So to motivate these tests then, the null hypothesis is that the coefficients are the same across all units. That is, they are stationary. We reject the null hypothesis if these p-values are smaller than 0.05, just as with most other 95% level hypothesis tests. So if these p-values are below 0.05, we can reject the null hypothesis that the coefficients are the same across all 67 units. As you notice, none of these p-values are below 0.05. Some of them are below 0.10. So with a 90% level of confidence, we could say that the coefficients vary across units that are non-stationary. That's with the fixed bandwidth. With the adaptive bandwidth, none of these come close to even the 0.10 level of statistical significance. So at this stage, strictly speaking, based on this randomization test, there is no reason to proceed with the geographically weighted regression. That is, these tests just told us that the coefficients do not vary across units in any statistically significant manner. Still, let's push ahead with the GWR analysis. There's some additional commands here that you can export the results from this Monte Carlo test. You could potentially also specify different bandwidths, but let's keep pushing forward. We'd like to pick our optimal bandwidth. So there are several options here. I've already introduced them, the fixed adaptive bi-square, fixed bi-square, adaptive Gaussian, fixed Gaussian, etc. The default is the adaptive bi-square, so let's just run the command with that. If you want some additional information on this command, you can run this help command here, but let's just generate the adaptive bi-square bandwidth with this block right here. So we just generated this object adaptive.bs1, and there are several other options that I've specified here. Option 2, a fixed bi-square, option 3, an adaptive Gaussian, and option 4, a fixed, sorry, that should be a fixed Gaussian. And let's run the analysis now with that one that we just selected. So that's step 9 here, the GWR models. Again, if you want some more help, there's the command. So we're going to generate this new object, GWR1, from the geographically weighted regression. There's our Y. Here are our predictors. Our bandwidth is adaptive.bs1. We're using a bi-square weight. Here are our coordinates, and we want to extract the hat matrix. So this will tell us which observations are more influential than others, etc. So we can run this, and you can see that it runs quite quickly with such a small sample size, and we could display the full results by calling GWR1. Here is GWR1. This set of results should be somewhat comparable to table 1. So this is what you would want to report alongside the OLS results if you were going to report a full version of table 1. You've got the minimum value. Remember that the coefficients now vary across every single unit. So looking at the coefficients, for instance, for the terrorism index, these results say that the minimum coefficient for T is negative 0.012, or negative 0.01 you could say. The maximum coefficient for terrorism, let's zoom in here. Excuse me. Let's zoom in up here. It's not zooming in where I would like it to zoom in. All right. So what is this saying? I'm just going to zoom out here just because it's not staying in focus. But this result is saying that the minimum value of the coefficient for T across any of the 67 units is minus 0.01. The maximum value is minus 0.002. That is the one that's closest to 0, right? It's still negative. But so terrorism always has a negative effect on economic growth. The median value is minus 0.003. This is the value you'd want to compare to the OLS estimate. The OLS estimate is the mean, right? So you probably want to look at these results alongside the results for OLS. So you could just type, remember the OLS object was called OLS1. So you could summarize OLS1. There's the estimate, right? The stationary estimate is minus 0.006. The median of the GWR estimates is minus 0.003, so they're slightly different. And then the interquartile range is this range from the first quartile or the lower quartile to the third quartile or the first upper quartile. So this is the interquartile range. 50% of the values estimated by GWR are within this range. We could compare this to, say, a 66% confidence interval of the OLS estimates. We've got some other model fit statistics here we could look at. You could compare these, if you wanted to the OLS regression, just as the authors do in table 1 here. Again, let's keep pushing forward here with the results so that we can say something meaningful about these results. We do want to get to the graphing and the post-GWR diagnostics, but since this video is already 30 minutes long, I'm going to stop here and continue with a second video in just a second.